Okay, in the interest of keeping this timely for everyone, we're going to go ahead and get started. Welcome. I'd like to thank you for joining us for today's webinar. My name is Scott Newman, and I'm the Director of Technical Sales and Applications here at Optiwave, as well as the project lead for the OptiFDTD product, which we'll be overviewing today. I would like to let you know that the chat and the Q&A are both open, so during the presentation, if you have any questions, please feel free to put them there. If we don't get to your questions during the session, we will certainly follow up through email. Today, we'll be discussing the modeling of the polarization beam splitter design that was proposed by a third party in a publication. Our goal is to provide you with valuable insights and practical takeaways on how you can model these kind of structures that you can apply in your own work or research. Before we get into the device itself, I would like to direct you to other reference material we have in your efforts to learn the product. The first is our knowledge base. If you go to optiwave.com, under support, there will be an option for our knowledge base. We are currently in the process of growing this database out. There are three types of articles. We have fundamental theory, which goes into the physics and the math behind the various techniques we use in our simulators. There's general structures that might demonstrate these capabilities. And then there are paper reproductions, which is what this particular webinar is looking at. The other thing to be aware of is we have a series of webinars, as well as webinars like this one here, that are recorded, and they are then made available on our YouTube channel. We have a channel called Optiwave HD. If you go to YouTube, I recommend searching for Optiwave HD specifically, as there are many folks out there that are giving tutorials on the OptiFDTD, the Optiwave product. So if you go into Optiwave HD, there will be a playlist for each of the products. You can go into that playlist and check things out. We have a wide range of applications and tutorials available. Coming back to the device in question, we're going to be looking at a polarization beam splitter presented by Mao et al. In Optics Express. The polarization beam splitter is a key component in integrated photonics. It's used to separate light based on polarization, ensuring that the TE and TM polarized light are routed to different paths with minimal loss. Polarization beam splitter devices are crucial for applications in communication systems, sensing, and quantum computing. Here, we'll introduce this specific design from the paper and analyze it. This particular structure is based on an SOI platform. So in this case, we're looking at symmetrical SOI background. We do not model the underlying silicon substrate, and the silicon structures are assumed to be in the device layer at 220 nanometers. This particular device takes advantage of two structures, a sub-wavelength grating, as well as a slot waveguide to try and get the mode matching operational and tuned to be able to do the performance that we desire, or that was desired by the author. The design and optimization of the structure can be found in the work as cited of Mao et al. And should be reviewed by those interested in this structure. My objective today is to demonstrate how this particular structure can be modeled within OptiFDTD. The design consists of three regions: the input region, which simply has the initial input waveguide; the coupling region, which has the sub-wavelength grating as well as the slot waveguide; and then the separation region, in which the two waveguides separate out so we no longer have any coupling. Within that, going back to that coupling region, we have the sub-wavelength grating. So the idea here is the sub-wavelength grating allows us to engineer and fine-tune the effective index of that particular waveguide. It is also tapered in order to minimize reflections as the waveguide interacts with this particular structure. And then, as I said, we have the slot waveguide up in the cross path to tailor it for the TM polarization. So the through section, the section with this sub-wavelength grating, is for our TE polarization, and the coupling region is tuned for the TM polarization. And just to be clear, TE in this case is EX dominant field, while TM is the EY dominant field. Just taking a look at those two sections again, we have the subwavelength grating. As I said, they're constructed, designed to fine-tune the refractive index, and we have a taper applied to it. On the through, we have the strip waveguide. Just double checking, our properties have actually hit all of these. The only thing to comment on here is that on the right table, we have the various properties that were used to generate these two structures. And the efficiency can be tuned using the number of subwavelength gratings units, the coupling length, as well as the separation between waveguides. So what we're going to do now is we are going to bounce over to the OptiFDTD product and discuss the waveguide and subwavelength grating design for this structure. Within OptiFDTD, you have control over your materials, and the materials, waveguides, components are all handled in the project browser here on the left. Under materials, we're currently using constant dielectrics. So if I open up the silicon dioxide, we can see that it has a refractive index of 1.44. And we also have our silicon, which is sitting at 3.47. We also have dispersive materials. You can add those and you can do actual fits to experimental data. For example, import something in from refractiveindex.info and you can do a fit. But for now, we are going to be running a CW simulation, single wavelength. We're not worried about dispersive performance. For waveguides, they are broken into two different structures. One is the profile, which are seen here. We have the one called the channel example, and the other is the fiber example. If you wish to create your own, you can certainly do so. These define the transverse profile of your waveguide. So if we open up the channel example, this one is fairly simple in the sense that we only have the one layer. These things are broken up into 2D. This should actually be silicon. So if you're running a 2D simulation, it's just going to use this value wherever the waveguide, this material gets assigned. But for 3D, we can actually define multiple layers, the width of those layers, the thickness of those layers. The interesting thing about this particular design that we are demonstrating here is the use of parameters. So you'll see here that the width of this waveguide is set to be some parameter known as WC, and the thickness of it is set to be H. Any entry window that has an f of x or an asterisk next to it indicates that it will allow you to use parameters. So you can see here, this particular design has widths set for each of the subwavelength gratings. That's the W1 through 28. And then we also have the periodicity of the subwavelength grating, the coupling length of the grating. These are all parameters that can be used. And then if you adjust the parameter, any of the design components that use that parameter can be adjusted automatically. So this is the waveguide profile. And then the second part of a waveguide is the actual waveguide itself. This controls the start position. And you'll notice that we are using equations along with parameters here, as well as the end position for that waveguide. We define its width. So this cannot actually allow you to scale your profile. So the largest width, the layer with the largest width has to match this width so the profile can be scaled. And we assign a depth, which is your Y, your in and out of the page in this case, in this view, the label, as well as the profile. So that's how waveguides are designed. Now you'll notice here, we have quite a few. We have 1 through 29, which represent each of the elements within the subwavelength grating. You could theoretically do these by hand and enter in each of these equations, but that would be tedious, particularly if you end up changing something that wasn't parameterized. So what we can actually do here is we can script the creation of this waveguide. So what we have here is the initial command deletes all of the waveguides because we don't want to create waveguides that are already there. We see calls to some kind of create waveguide function, which I'll talk about in a moment, where the SI waveguide, which is the input, the output waveguide, the coupled SI waveguide, as well as the slot for that coupled waveguide, are all created. We also have the S-bend. So these 5 objects that get created represent this waveguide here, the slot, the input, the S-bend, and then the output. But what you'll see for the sub-wavelength gratings is we have a for loop here, and we run it for 29 instances, and each one of those has functions that control the name that gets added to it and its start and end positions. That's what where the index of the for loop modifies it. The create waveguide function is down here. This is where we create the handle to that waveguide, and we set all of its respective properties. So you can see each one of these, while you could edit it manually, are actually created by the script to make things easier. The easiest way to learn these functions and know what's available to you for those is create your design and then come over here. I'm going to copy this so I don't lose it. If we come over to layout script and hit yes, you will see that this will create a series of commands for the creation of each object within the design. So we have each of the waveguides, including all of these for the sub-wavelength grading elements. And if we come down to the bottom, we also see commands for our input plane. That's the easiest way to start learning the VB script. That's the language we use for our scripting engine. And that is how you create waveguides and structures. This is how this particular structure got created within the FDTD product. Now, the refractive indexes for the actual materials that are used, so the silicon dioxide as well as the silicon, are both shown here. But what's more important is the effective indices of these waveguides. The waveguide's excited using a modal input field, which we'll talk about in a moment. And within the solver parameters, these can be set. So the solver parameters can be set to those in the bottom right-hand table there for the FEM. And what it will do is it will calculate the mode distribution for us. But more importantly, it will also give us the effective refractive indices. So for example, for that TE waveguide, which we see on the top left is 2.58, while the one on the right is 1.86. So that is our input plane. So we'll pop back over to the product to show that input plane. Input plane is this red structure right here. If we open it up, you have the general properties for the waveguide, how you want your transverse field to be. This could be a modal, which we're using in this case, but it could also be Gaussian, rectangular. We also support user-defined fields. These are our internal format, but you can convert many formats to them. We have tools available within our OptiTools folder, which comes installed with your product, which can convert some of the ray tracing applications, their results, over to our F3D format. But for now, we're going to use a modal. You have control over your Z position, your initial phase, direction. The operating wavelength for this one is going to be 1.55. We are also going to run as CW. So it's purely going to be the 1.55 microns. And if you wanted to do a broadband simulation, you could make your input a pulse. By making it a pulse in time domain, you get a spectrum in frequency domain. This is excellent for any time you want to look at transmission or reflection spectra, instead of having to run multiple simulations for each wavelength like you would in a frequency domain simulation. We can actually get all of this information from one simulation. You'll have to normalize for the input power at each wavelength, but the product has all of that built in. Looking at the actual mode injection, if we go to the 3D, so this is where we set our general properties. If we go to 3D transverse, that's where we control our transverse. Under this section, you control whether you want to deal with amplitude or power. In this case, we have set our amplitude to 1, but we could just as easily edit our power. When you click on Find Modes, you will get an option to use one of the 3 built-in mode solvers that are available through OptiMode. So when you install OptiFDTD, OptiMode is also installed and is interfaced with FDTD. So if we choose FEM, we then have to choose whether we want to use a cross-section slice or a waveguide selection. Both of these will do the same thing for this particular design. The cross-section slice will take the refractive index of anything that crosses the input plane, and anywhere that doesn't have anything that crosses, it gets set to the background material. This is good if you have multiple waveguides or odd geometry and you want to inject along that. The waveguide selection is if you specifically want to inject in that waveguide and don't want to consider the other structures. What will happen is you take that waveguide. So for example, if we select our waveguide, it will take that waveguide and assume background for everything else and then do the mode solve. So if we hit calculate mode, we will see a new panel come up. And this panel here is exactly the same panel you would see if you were working directly with an OptiMode. And these are the properties for the FEM mode solver. So those were the properties that were shown in the table in the previous slide is what we enter in here. The thing that you're going to change the most often is this right here, your modal index. Typically, it is set to use the highest index that's available within the design, which one would assume is where your mode is going to be. However, there are instances where, for example, in a slot waveguide, your mode is actually going to be in the slot. So its modal index is going to be much closer to the background as opposed to the refractive index of the material, or not the background, but the material in the slot. So often you will see removing this checkbox and putting in what you believe the mode index should be. It will be used as the initial guess as part of the FEM solver. You can then specify the number of modes. The thing to keep in mind when you're using this in Opti mode, this specifies how many modes it will show you. When it is being used as an interface to FDTD, this is how many modes it will solve, but you have to be aware that the last mode is the one that will be injected. So what you'll see here, and I'll show in a moment, the TE is the fundamental mode of the input waveguide. That's the one that's going to be found first. So you'll see here we have number of modes is 1 for this particular design. And then if we open up the TM simulation, just give it a moment to open. You will see that the number of modes that are specified for that is 2, because we want to actually use the second mode, which is the TM polarization. So that's how you control which mode actually is injected in this using this source. Then we back to TE, that's our input plane. So let's discuss the structure and why we use the sub-wavelength grading and the slot waveguide. So for coupling to occur, it's necessary for the modal index to match between the 2 waveguides in the coupling region. So this waveguide with the sub-wavelength grading, as well as the slot waveguide. However, you want to be able to calculate the effective index of this subarray wavelength in order to start doing that matching. As the grading is sub-wavelength, we can illustrate the coupling through effective index matching by using effective median theory to model the sub-wavelength grading. This will allow us to turn this waveguide into effectively a slot waveguide, and we can compare it to the existing slot waveguide. The refractive index for slot within the equivalent slot waveguide, that actually represents the sub-wavelength grading, is derived using the formula here, which is this one. So we have the refractive index of the silicon, refractive index of the silicon dioxide, and then we have a filling fraction. here. And what we see is that it is now possible to consider the effective index of the two waveguides, and we can begin tuning. So this sub-wavelength grading is now converted to an equivalent slot waveguide, and then we can compare it to the actual the cross waveguide, which is a slot waveguide. And what we will see when we do the analysis of these two structures within OptiMode, we will see that the TE polarization has different effective indices in these two waveguides. It's 2.13 in the equivalent slot waveguide, while it is 1.84 in the cross slot waveguide, which is fine. We don't want the TE to couple between these two waveguides. We want it to perceive through. The TM polarization, on the other hand, has the same effective index between these two waveguides. So we have effective index matching. So long as we bring the waveguides close enough together, we will actually get coupling across into the cross waveguide and then separation of the polarizations. The one thing I do want to talk about here is some of the simulation settings that are required to model a structure of this nature. Most of the properties are applicable to all of the structures that you would model in FDTD, so I'll talk about those separately in a moment. The one I want to talk about here is the capability of doing non-uniform mesh. So this particular structure has a number of characteristics that there are certain regions where you are going to want quite high resolution, and then there are regions where you do not. For example, this is an SOI waveguide. We don't need high resolution in the SiO2 layers. However, within that thin 220 nanometer device layer, you're going to need high resolution. So what we can do here with the non-uniform mesh is we can set up regions of high resolution and regions of lower resolution so that we can get the resolution we need while keeping computational resources as little as we can. So we're going to pop over into the product, and I'm going to talk about those simulation parameters now. And I will also be discussing the observers that we use for this particular product. So simulation parameters. The first thing you see within your simulation parameters is the spatial discretization. So this would be the uniform discretization if we weren't using the non-uniform mesh. This is your spatial spacing for all three axes. If auto is checked, it is doing 1/10 of a wavelength in the highest index material as the auto setting. But as you would imagine, considering for the through waveguide, we're using sub-wavelength geometry, 1/10 of a wavelength probably is not a high enough resolution. So you remove the auto setting and then you can specify your own refractive index spacing for your mesh. Under advanced, we can control our boundary conditions. For most applications, customers typically use our perfectly matched layers, which is what this one is set for here. But you could also use our electric conductor, magnetic conductor, or the periodic boundary conditions. Going into more discretization issues, the time parameters, there are two. One you should never really touch unless there's a very good reason for doing so. This is your time step size. This is set by the coronal stability condition for FDTD simulations. This is a function of how fast it takes the energy to get out of the cell relative to the time the simulation is running. So if you violate this condition, your simulation will not be stable and the results will be divergent and likely overflow one of your variables. So if you take it off auto, which by definition matches the stability criteria, if you take it off auto and change it, you have to change it to a value that is in fact smaller than the auto setting. If it goes smaller, it will remain stable. If you make it bigger, it will not. The other discretization concern to be aware of is the number of time steps. This is the duration of the simulation within the simulation space. This is set to auto right now. That's fine for this design. What the auto does is it takes a look at the longest distance that the light could travel. So it's from opposing corners and how long it would take to travel that distance in the highest index material. This is fine for any structure without resonance or with a low Q. But as soon as you start getting into resonators, Fabry-Perot cavities, anything that can have any reasonable Q factor, what you will find is the light bouncing back and forth within that resonant structure is going to need more time for the light to propagate through and get to whatever your output is. So typically anything with any kind of Q factor, you're going to remove this auto and you're going to be adjusting this setting. So the question that gets asked most often is how many time steps do we need? How do you figure that out? And the answer to that is observation points. So I'll touch on that when I take a look at our observers. This here non-uniform mesh is what we were talking about for these structures that have really fine regions and really coarse regions. So if we hit parameters, you can now specify your regions for each of the directions. So for the X direction, which is the vertical in this particular view, you'll see that we have higher resolution from -1 to 1. So it is covering this region where the waveguides are. Where there are not the waveguides, we allow it to be more coarse. So in the coarser regions, we see it is 50 nanometers, while in the fine resolution regions, it is 5 nanometers. And if you want to see how that varies, you can see that there is a function that is used to change from the coarse region down to that fine region. Similarly, our y-axis, we are setting our high resolution to be in and around the device layer for the SOI. And then for the Z, it's really just the whole length of it. There are instances where you could run a much higher resolution for just this coupling region, but for our purposes, it didn't really benefit that much. Hit OK here, and that is it for simulation parameters for this particular structure. Now, this one doesn't have the observers because it was demo. This is the TM simulation. It does still have its observers. So I'm going to talk about those briefly for a moment here. The observation areas can exist on any of the planes. So the the XY, the XZ, and the YZ. The XZ is typically used for looking at propagation as a function of like distance. The XY and is mostly the other one that is used, and that is used for monitoring, for example, in this case, reflection. And in this case here, there are two. One is across the cross waveguide and one is across the through waveguide. So these are for monitoring the output of that. The other observer that exists here that I want to touch on is this observation point. See this quantity right here? Actually, I'm going to move. You can change the order of your observers just so things are not overlapping. So now we can see our structures. This observation point right here. So our observers, the observation lines and the observation areas are given cumulative DFTs at every time step. So what you get at the end of the simulation is an average of your results, while the observation point is actually storing the field as a function of time for that single grid point. We can't do that over areas because the amount of data you're collecting is substantial. So we have this observation point, and this observation point is how I determine how many time steps to use. So I'll run a simulation, we'll take a look at the observation point, and then based on that, I will either run a much longer simulation or I will proceed with my analysis. So those are our simulation settings as well as our observers. Just gonna pop back over to the slides. So what we have here is those field results being reported by that XZ observation area. At the left and right, we have the TE and TM polarizations. from the simulation, so the two different simulations. The TE being our EX component and the TM being our EY component. The design does ensure effective polarization separation by tailoring the mode overlap in that coupling region, as we've been discussing. So we can see this because in the TE iteration, there is almost no power visible qualitatively within the observation cross waveguide. And then for the TM waveguide, there is very little power within our through waveguide. So we're going to take a look at those results a bit more carefully now. Bear with me a moment while I open up the results file. So when you install OptiFDTD on your system, you will get, in addition to OptiMode, you will get two products. One is the OptiFDTD Designer, and the other one is the Analyzer. Designer is the product we've been in up until now, where we're setting up our simulation, the properties, the parameters, the geometry. Once the simulation is run, you then have Analyzer for taking a look at those results. As stated before, the first thing I always do is take a look at my observation point. And what we're looking for here is one of two things. For a CW simulation, what we're looking for is that it is starting to oscillate consistently. We want to make sure we are far away from this ramp up region. So we have got multiple cycles done past the ramp up, and it is now stable. In a pulse simulation, what you would want to see is you would want to see your pulse and see it fully decay. Now, in a resonance structure, you got to be aware that you're going to see a pulse, see it decay, then you're going to see another pulse, decay, another pulse, decay, as you have those round trips through your resonator. So you basically want to make sure that as much power is out of the simulation domain as possible so that the observers can have had a chance to collect that information. So that's what the observation point is used for. Then we can take a look at the XZ, which is that top-down view. So we're looking at the TE. So this is the EX dominant, but we could also look at the EY and the EZ components of the field. Qualitatively, we see that the dominant part of the field is staying in the through waveguide. We do see some oscillation here. This is a result of the staircasing in the bend. We could have run a higher resolution region in the bend to tone that out, but that is what we're observing there. If you want a more qualitative assessment of what your output is, we can take a look at the slot waveguide, and we can take a look at the power that is being propagated. This is the actual power in watts, and this is the power as a function of the input. So we can actually see that we're only looking at 3% of the input was propagating over to the slot waveguide, while in the grading output, we are seeing most of the power. So that is, so you can take a look at our input. We can take a look at reflection behind the input plane. The thing to keep in mind with this negative here is that it's not negative power. It's simply a function of the direction of the light. So as the light is propagating as a reflection in the negative Z direction, we are going to have that sign, and that's where the negative comes from. And that is all of the observers there. And we pop back over to our slides. So as we promised, we demonstrated the design and simulation of a polarization beam splitter using a subwavelength grating and a slot waveguide. We've demonstrated the design of it as well as the simulation and the results of that particular structure. For anyone who has any questions on this structure, or OptiFDTD in general, you can feel free to send myself an email, scott.newman@optiwave.com, or you can send it to the general support account at support@optiwave.com, and either myself or one of our team will respond.